there is a quiet boundary to everything we can see. Not a wall, not an edge in the traditional sense, but a limit shaped by time itself. A horizon defined not by distance alone, but by how long light has had to travel since the beginning of the universe. When we look out into space, we are not simply looking far away, we are looking back. Every star, every galaxy, every faint glow in the darkness is a message sent across time, arriving only now after journeys that span millions or billions of years. This is what defines the observable universe, everything whose light has had enough time to reach us. Beyond that, there may be more, far more, but it remains hidden, not because it does not exist, but because its light has not yet arrived. Today, that boundary stretches to around 46 billion light-years in every direction, and yet the universe itself is only 13.8 billion years old. At first, this seems impossible. How can we see something farther away than the age of the universe would allow? The answer lies in the nature of space itself. The universe is not expanding into something. Space itself is expanding. As light travels across the cosmos, the fabric it moves through stretches, carrying distant galaxies even farther away. What we observe is not where those galaxies are now, but where they were when their light began its journey. The edge we perceive is not a physical boundary, it is a limit of information. This horizon is often described as the particle horizon. It marks the maximum distance from which light has been able to reach us since the beginning of time. Beyond it, there are undoubtedly more galaxies, more structure, perhaps entire regions similar to our own, but they remain hidden behind a boundary that is not solid, but temporal. There is also another limit, more subtle but equally important. The event horizon does not describe what we can see, but what we will never see. There are regions of the universe moving away from us so quickly that any light they emit now will never reach us, no matter how long we wait. In this sense, parts of the universe are already lost to us, not destroyed, but permanently disconnected. Alongside this is the Hubble horizon, a boundary tied to the rate at which the universe expands. Beyond this distance, galaxies recede from us faster than the speed of light, not because they are moving through space at such speeds, but because space itself is stretching between us. It creates the illusion of a race, light traveling toward us while the universe expands beneath it, pulling its source farther away. In some cases, the expansion wins, and the light never arrives. This is why the night sky is not filled with an endless blaze of stars. There are limits to what can reach us, limits imposed not only by distance, but by the history and expansion of the universe itself. Even the light we do see carries another truth. When you look at the sun, you see it as it was 8 minutes ago. The nearest stars appear as they were years ago, and distant galaxies as they existed billions of years in the past. The deeper we look, the further back we travel, until eventually we reach the oldest light that can be observed. This faint glow fills the entire sky, invisible to the human eye but detectable with sensitive instruments. It is the cosmic microwave background, a remnant from a time when the universe was only a few 100,000 years old. Before this moment, the universe was opaque, a dense hot plasma where light could not move freely, constantly scattered in a kind of cosmic fog. As the universe expanded and cooled, atoms began to form, and light was finally able to travel across space without obstruction. What we detect today is that first release of light, stretched over billions of years into the microwave part of the spectrum. It surrounds us in every direction, a quiet echo of the beginning. Within it are tiny variations in temperature, small differences that would eventually grow into galaxies, clusters, and the vast cosmic web that defines the structure of the universe. From this faint radiation, scientists have been able to reconstruct the story of the universe's origins, its composition, and its evolution. We now understand that everything we can see, stars, planets, galaxies, makes up only a small fraction of what exists. Most of the universe is composed of dark matter and dark energy, invisible forces that shape its structure and drive its expansion. And yet, despite everything we have discovered, we remain confined. Every observation, every image, every piece of knowledge exists within this single horizon, a sphere of visibility defined by light and time. Beyond it, the universe continues, but for now, it is unreachable. Not because we lack the technology, but because the universe itself has set the boundary. And so the question remains, as it always has. If this is all we can see, what lies beyond it? If the universe places a limit on what we can see, it does not entirely close the door on what we can understand. There are ways, indirect and often extraordinarily subtle, that allow us to gather information from regions far beyond our visible reach. Light may define the boundary of the observable universe, but it is not the only messenger that travels across the cosmos. There are particles so small, so elusive, that they pass through entire planets as if they were empty space. These are neutrinos, fundamental particles produced in enormous quantities by some of the most energetic processes in the universe, nuclear reactions inside stars, supernova explosions, and even the earliest moments after the Big Bang itself. What makes neutrinos remarkable is not just their origin, but their behavior. They interact so weakly with matter that billions pass through your body every second without leaving a trace. For most of their journey, they travel almost completely undisturbed, carrying with them information from places that light cannot easily escape. While light can be absorbed, scattered, or trapped, neutrinos move almost freely, crossing vast cosmic distances without interference. In principle, they can bring us signals from regions far beyond our current observational limits, offering a glimpse into events that would otherwise remain hidden. The challenge, however, lies in detecting them. Because neutrinos interact so rarely, capturing even a single one requires immense detectors, often buried deep underground or beneath ice, shielded from other forms of radiation. These instruments are designed to wait, patiently, for the faintest sign of interaction, a tiny flash of energy that reveals a neutrino has passed through. It is a slow and difficult process, but with each detection, we expand our ability to observe the universe in a completely different way. Not through light, but through particles that ignore most of the obstacles light cannot overcome. Alongside neutrinos, there is another messenger, one that does not travel through space, but within the structure of space itself. Gravitational waves. These are ripples in spacetime, produced when massive objects accelerate, such as when black holes collide or neutron stars spiral into one another. Unlike light, which can be blocked or weakened, gravitational waves pass through matter almost entirely unaffected, carrying with them a direct imprint of the events that created them. By the time these waves reach Earth, they are incredibly faint, stretching and compressing space by distances smaller than the width of an atom. Detecting them requires instruments of extraordinary precision, capable of measuring distortions so small they seem almost impossible to observe. Yet in 2016, humanity achieved exactly that. For the first time, gravitational waves were directly detected, confirming a prediction made a century earlier. The signal came from a collision between two black holes more than 1 billion light-years away, a violent event that released more energy in a fraction of a second than entire galaxies. What reached us was not light, but a distortion in space itself, a subtle vibration that carried information across the universe without being diminished in the same way as electromagnetic radiation. Together, neutrinos and gravitational waves offer something profound. They allow us to observe the universe in ways that do not rely on light, extending our reach beyond traditional limits and giving us access to phenomena that would otherwise remain invisible. But even with these tools, there is a boundary we cannot cross. The expansion of the universe continues to impose limits that no technology can overcome. There are regions so distant, moving away so rapidly, that no signal sent today will ever reach us. Not light, not particles, not even gravitational waves. These regions are not just hidden, they are causally disconnected. No information from them can ever influence us, and nothing we do can influence them in return. In this sense, the universe is not just vast, but partitioned, divided into regions that are forever separated by the expansion of space itself. And yet, the boundary is not static. As time passes, light from more distant regions continues its journey toward us. Slowly, almost imperceptibly, the observable universe grows. Objects that were once beyond our reach may eventually become visible, their ancient light finally arriving after billions of years of travel. At the same time, other regions slip away. Galaxies that are currently visible will, in the distant future, recede beyond our event horizon. Their light will stretch, fade, and eventually disappear, leaving behind a darker, emptier sky. So, while our view of the universe expands in one direction, it contracts in another. We gain access to deeper layers of the past, while the present universe slowly withdraws from us. It is a quiet, ongoing separation, one that unfolds over billions of years, shaping not only what we can see, but what we will ever be able to know. And this raises a deeper question. If the universe is gradually hiding itself from view, if more and more of it becomes unreachable with time, then what does the future of this cosmic horizon look like? What happens when the observable universe itself begins to shrink? The universe is not only vast, it is dynamic. Every moment, every second, it changes, quietly reshaping itself on scales so large that the transformation is almost impossible to grasp. What we see today is only a temporary snapshot, a brief frame in an ongoing process that stretches far beyond human timescales. To understand where this is all heading, we have to move forward, not just thousands or millions of years, but billions, trillions, and beyond. In the relatively near future, on cosmic terms, the changes begin slowly. The galaxies around us continue their motion, bound together by gravity, forming what we call the local group. Among them is Andromeda, a massive spiral galaxy drifting steadily toward the Milky Way. Over the next few billion years, these two galaxies will collide and merge, not in a violent crash, but in a gradual dance of stars, reshaping both into a single larger structure. At the same time, the universe continues to expand. This expansion is not slowing down. In fact, it is accelerating, driven by a force we still do not fully understand, known as dark energy. As space stretches, distant galaxies move farther and farther away, and the light they emit becomes increasingly redshifted, stretched into longer wavelengths. For now, this expansion is subtle on local scales. Gravity still dominates within galaxy clusters, holding them together. But over larger distances, expansion wins. Galaxies that are not gravitationally bound to us are slowly slipping away, crossing the boundary beyond which their light will never reach us again. Billions of years pass, and the effects become more pronounced. Our Sun, the source of all life on Earth, begins to change. As it ages, it grows brighter and hotter. The balance that has allowed life to exist for billions of years begins to shift. Oceans evaporate, the atmosphere transforms and the surface of the planet becomes increasingly hostile. Eventually, the Sun expands into a red giant, engulfing the inner planets, possibly including Earth itself. What was once a thriving world becomes part of a much larger stellar envelope, its identity erased in the slow evolution of its parent star. But this is only a local story. Beyond our solar system, the universe continues its broader transformation. Star formation begins to decline. The vast clouds of gas and dust that once gave birth to new stars are gradually used up or dispersed. Without this raw material, fewer stars are created, and the night sky slowly changes. Where there were once countless bright, short-lived stars, there remain older, cooler ones. Over time, even these begin to fade. The universe enters what is often called the era of degenerate stars, a time when the dominant objects are no longer luminous suns, but remnants, white dwarfs, neutron stars, and black holes. Trillions of years into the future, star formation effectively comes to an end. The cosmos grows darker. Galaxies, once vibrant with light, become collections of fading stellar corpses. Occasional collisions and interactions may still occur, sometimes reigniting brief bursts of star formation, but these events become increasingly rare. Meanwhile, the expansion of the universe continues to accelerate. Distant galaxies disappear from view entirely, not because they have ceased to exist, but because their light can no longer reach us. The observable universe shrinks in terms of what is accessible, even as the total universe continues to grow. Eventually, observers within any given galaxy will see only their local cluster. Everything beyond it will have faded into darkness, carried away by the expansion of space. The universe becomes isolated. As time stretches further, even the remnants begin to change. White dwarfs cool and fade, becoming black dwarfs, cold, dark objects that emit almost no radiation. Neutron stars lose energy. Black holes, once the most enduring structures in the universe, begin an incredibly slow process of evaporation through what is known as Hawking radiation. This process is unimaginably slow, taking timescales far beyond trillions of years. But given enough time, even black holes will disappear, releasing their remaining energy back into the universe. What remains is a cosmos dominated by low-energy particles, photons, neutrinos, and a scattering of the most stable remnants of matter. The temperature continues to fall. Energy becomes evenly distributed, and the differences that once drove structure, stars, galaxies, life itself, begin to vanish. This is the path toward what is known as heat death. Not an explosion, not a dramatic ending, but a gradual fading. A universe that approaches a state of maximum entropy, where no useful energy remains to power processes or create structure. It is a quiet ending. A universe that does not collapse or tear itself apart, but simply runs out of the ability to change. And yet, this may not be the only possibility. The future of the universe depends on the balance of forces that govern it, particularly the relationship between gravity and dark energy. If that balance were different, the outcome could be very different as well. In one scenario, the expansion continues to accelerate until it becomes overwhelming. Galaxies are pulled apart, then stars, then planets, and eventually even atoms themselves. This is known as the Big Rip, a scenario in which the fabric of the universe is stretched to its breaking point. In another possibility, if gravity were to regain dominance, the expansion could slow, stop, and reverse. The universe would begin to contract, drawing galaxies back together, increasing in density and temperature until everything collapses into a state similar to the one from which it began. But current observations suggest that expansion is accelerating, not slowing, which means the slow fading, the long, quiet descent into darkness, remains the most likely path. And as we consider this future, stretching across timescales so vast they defy intuition, a deeper realization begins to emerge. The universe is not static. It is not permanent. It is a process, one that began, evolved, and will eventually reach an end, even if that end is measured not in years, but in trillions upon trillions of them. And if the future leads toward darkness and isolation, then what about the structure we see today? The vast cosmic web, the clusters of galaxies, and the enormous empty regions that lie between them. What role do they play in this evolving universe? And why does so much of it appear to be empty? As the universe evolves on these immense timescales, its structure reveals something just as fascinating as its fate. When we step back and observe the cosmos on the largest possible scale, we begin to see that galaxies are not scattered randomly through space. Instead, they form an intricate pattern, a vast cosmic web made up of dense clusters, long filaments, and enormous regions of apparent emptiness that stretch across unimaginable distances. These empty regions are known as cosmic voids, and despite their name, they are not truly empty. They are simply areas where matter is far less concentrated, places where galaxies are sparse, sometimes numbering only a few dozen where tens of thousands might be expected. In contrast to the bright, crowded clusters of galaxies, voids appear as immense dark expanses, creating a striking contrast that defines the large-scale structure of the universe. The existence of these voids was not immediately obvious. Early astronomers, limited by the reach of their instruments, could only map the stars within our own galaxy. It was only with the development of more powerful telescopes and large sky surveys that the true distribution of galaxies began to emerge. As astronomers plotted the positions of galaxies in 3 dimensions, a pattern became clear. Matter was not evenly spread, but instead arranged into a network, with vast gaps in between. These gaps, once thought to be observational errors or anomalies, were eventually recognized as fundamental features of the universe. They are not simply empty spaces left over by chance, but essential components of the cosmic web, shaped by the same forces that formed galaxies and clusters. Some of these voids are so large that their scale is difficult to comprehend. There are regions where, if you were to travel at the speed of light, it would take hundreds of millions of years just to cross from one side to the other. Entire volumes of space where galaxies are so rare that the night sky, if viewed from within, would appear almost completely dark. One of the most well-known examples is the Boötes void, a region so vast and so underpopulated that it has been described as a cosmic desert. In a space where thousands of galaxies might normally exist, only a small number can be found. Its sheer emptiness challenges our intuition about how matter should be distributed across the universe. Even larger structures exist. Supervoids span distances of up to 1 billion light-years, making them some of the largest known features in the entire cosmos. These regions are not perfectly empty, but their density is so low that they stand in stark contrast to the surrounding cosmic structures. Their presence raises important questions about how such enormous imbalances in matter distribution could have formed. To understand their origin, we have to look back to the earliest moments of the universe. Shortly after the Big Bang, the universe was not perfectly uniform. Tiny fluctuations in density existed, small variations in the distribution of matter and energy. Over time, gravity amplified these differences. Regions with slightly higher density attracted more matter, growing into galaxies and clusters, while less dense regions lost matter to their surroundings, gradually becoming the voids we observe today. This process, unfolding over billions of years, gave rise to the cosmic web. Matter flowed along invisible filaments, drawn together by gravity, leaving behind vast empty regions where little material remained. In this way, voids are not anomalies, but natural outcomes of the same processes that created structure in the universe. Dark matter plays a crucial role in this formation. Although it cannot be seen directly, its gravitational influence shapes the large-scale structure of the cosmos. It forms the scaffolding upon which galaxies are built, guiding the flow of ordinary matter into clusters and filaments. Where dark matter is less concentrated, voids emerge. At the same time, dark energy contributes to their growth. As the universe expands, this mysterious force accelerates the separation of structures, effectively stretching the voids and making them larger over time. Galaxies are pushed away from these low-density regions, further deepening the emptiness. Despite their apparent simplicity, voids are among the most challenging structures to study. Their low density means there is less visible matter to observe, making it difficult to gather detailed data. Yet they are incredibly important. By studying voids, scientists can test models of cosmology, refine our understanding of dark matter and dark energy, and gain insight into how the universe evolved on the largest scales. Some theories even suggest that voids may hold clues to more exotic possibilities. Because they represent regions where matter is scarce, they provide unique environments for testing the fundamental laws of physics. In these vast, quiet spaces, subtle effects that are masked in denser regions may become more apparent. There are also more speculative ideas, suggesting that voids could be connected to deeper features of the universe, perhaps linked to the earliest quantum fluctuations that shaped the cosmos, or even to structures beyond our observable reality. While these ideas remain unproven, they highlight how much we still do not understand about these immense regions. What is clear, however, is that voids are not simply empty gaps. They are an essential part of the universe's architecture, shaping the way galaxies form, evolve, and move. Without them, the cosmic web would not exist in the form we observe today. And as the universe continues to expand, these voids will grow even larger. Galaxies will drift farther apart, clusters will become more isolated, and the contrast between dense regions and empty space will become even more extreme. In the far future, the universe may appear far more fragmented than it does today, with vast distances separating the remaining structures. This leads us to an even deeper question. If such enormous regions of emptiness can exist within our universe, shaped by the earliest moments of its formation, then what does that say about the nature of the universe itself? And more importantly, what does it suggest about what may have existed before it began? As we trace the structure of the universe outward and the timeline forward, a deeper question begins to take shape, one that does not look ahead, but back, beyond everything we have already explored. If the universe has a history, if it has evolved and expanded and continues to change, then it must have had a beginning. And with that comes the question that sits at the edge of physics and philosophy alike. What, if anything, came before it? The Big Bang is often described as the origin of the universe, a moment when space, time, and energy emerged from an extremely hot and dense state. But this description, while accurate within our current understanding, does not necessarily mean it was the absolute beginning of everything. It may instead mark the beginning of the universe as we know it, the point beyond which our current laws of physics can no longer reliably describe what happened. One of the most important challenges in answering this question lies in the fact that time itself is tied to the universe. According to our best models, time did not exist independently before the Big Bang. It emerged alongside space, meaning that asking what happened before may not be meaningful in the way we usually think. This idea is captured in one of the more elegant proposals in modern cosmology, often referred to as the no-boundary model. In this framework, the universe does not begin at a sharp edge or singular point, but instead behaves more like a curved surface. Just as the surface of the Earth has no edge, yet is still finite, the universe may have no true beginning in time, only a smooth transition from one state to another. In this view, the Big Bang is not an explosion from nothing, but a boundary condition where our familiar concept of time begins to take shape. Other models take a different approach and suggest that our universe may be part of a much larger, ongoing process. One such idea is the concept of a cyclic or oscillating universe. In this scenario, the universe expands over billions or trillions of years, eventually slows, and then reverses, collapsing back into a dense state. This collapse, sometimes referred to as a big crunch, could then trigger another expansion, creating a new universe. In this sense, the Big Bang would not be a unique event, but one phase in an endless cycle of cosmic evolution. A related idea, known as the Big Bounce, refines this concept further. Instead of collapsing into an infinite singularity, the universe reaches a minimum size and then rebounds due to quantum effects. This avoids the problem of infinite density and suggests that our expanding universe may have emerged from a previous contracting phase. Rather than a true beginning, the Big Bang becomes a transition point between two eras. There are also models rooted in quantum mechanics that approach the problem from a completely different direction. In these, the universe may have originated from what is known as a quantum fluctuation. At extremely small scales, the vacuum is not truly empty, but filled with temporary fluctuations of energy where particles and antiparticles briefly appear and disappear. Under certain conditions, one of these fluctuations could grow, expanding rapidly and giving rise to an entire universe. In this picture, our universe would be one of many possible outcomes, a region where a small fluctuation expanded rather than collapsed. It does not require a traditional beginning, but instead emerges from the underlying properties of quantum fields. Expanding on this idea leads to the concept of the multiverse. If quantum fluctuations can produce universes, then it is possible that this process happens repeatedly, creating countless separate regions, each with its own physical properties. Our universe would then be just one among many, a single bubble in a much larger cosmic landscape. While this idea is compelling, it remains highly speculative. The challenge lies in testing it. If other universes exist but cannot be observed or interacted with, then confirming their existence becomes extremely difficult. For now, it remains a theoretical extension of our current models, rather than an established part of cosmology. Another intriguing possibility comes from the study of black holes. These objects, formed from the collapse of massive stars, contain regions where density becomes extreme and our understanding of physics breaks down. Some theories suggest that the interior of a black hole could give rise to a new expanding region of space, effectively forming a new universe. In this view, our universe itself could be the interior of a black hole that exists within a larger parent universe. This idea connects the smallest scales of quantum physics with the largest structures in cosmology. But like many theories in this domain, it remains difficult to verify. Across all of these models, one theme remains consistent. The closer we get to the beginning, the less certain our understanding becomes. Our current theories, general relativity and quantum mechanics, work extremely well within their respective domains, but they are not yet fully unified. The conditions at the earliest moments of the universe require a theory of quantum gravity, something that scientists are still working to develop. Until such a theory is complete, the true nature of the beginning remains open. It may be that the universe had no beginning in the way we imagine. It may be one phase in an endless cycle, or one of many in a vast multiverse, or the result of processes that occur naturally at the quantum level. Each possibility offers a different perspective, but none can yet be confirmed with certainty. What we can say is this: the universe, as far as we can observe, has a history that begins with the Big Bang and evolves into the complex structure we see today. Beyond that point, our knowledge fades, replaced by models, ideas, and possibilities that extend beyond direct observation. And yet, even without definitive answers, the search itself continues to push the boundaries of what we understand. From the limits of the observable universe to the deepest questions about its origin, each step reveals not only how much we have learned, but how much remains unknown. And perhaps that is the most enduring aspect of the universe. Not just its scale, or its age, or its fate, but the fact that no matter how far we look, or how deeply we question, there is always something beyond the horizon of our understanding. As we step back from these ideas, from horizons we cannot cross, from futures that stretch beyond comprehension, and from beginnings we cannot fully define, a quieter perspective begins to emerge. The universe is not something we observe from the outside. We are part of it, shaped by the same processes that formed stars, galaxies, and the vast structures that stretch across space. The atoms within us were forged in ancient stellar cores, scattered across the cosmos, and eventually gathered into the form we now inhabit. In that sense, our existence is not separate from the universe's story, but a continuation of it. And yet, despite this connection, our view remains limited. Everything we know is confined within a horizon defined by light and time. Beyond it, the universe continues, but it does so without us. Entire regions exist that we will never see, never interact with, never influence. Not because of distance alone, but because of the way the universe itself evolves, expanding, stretching, and gradually separating one region from another. Over time, this separation becomes more profound. Galaxies beyond our local group will continue to drift away until their light fades completely from view. Future observers, billions or trillions of years from now, may look into the sky and see only their own galaxy, unaware that a vast universe once surrounded them. The evidence of expansion, the cosmic microwave background, even the knowledge of a beginning, may all become impossible to detect. The universe will not just grow quieter, it will become harder to understand. In this distant future, the clues that allowed us to reconstruct the story of the cosmos will slowly disappear. The sky itself will change, not through sudden transformation, but through gradual loss. Light will stretch, signals will fade, and the observable universe will shrink to a small, isolated region surrounded by darkness. And yet, even as the universe moves toward this state, the questions remain. What lies beyond the horizon we cannot cross? What preceded the moment we call the beginning? And what ultimately defines the limits of reality itself? These are not questions that can be answered easily, and perhaps not ones that can be answered at all. But they continue to drive exploration, shaping the way we study the universe and our place within it. What we have discovered so far is only a fraction of what exists. A thin layer of understanding built on observation, theory, and inference. Beyond that layer lies uncertainty, not as a failure of knowledge, but as an invitation to continue searching. Because the universe does not reveal itself all at once. It unfolds gradually, across generations, through new tools, new ideas, and new ways of seeing. What is hidden today may become clear in the future, just as what once seemed unknowable has already become part of our understanding. And even if there are limits we can never overcome, boundaries set by the nature of space and time, they do not diminish the significance of what we have learned. Instead, they give it context. They remind us that knowledge is not about reaching an end, but about extending the horizon. Each discovery pushes that horizon outward, even if only slightly, revealing a little more of the structure, the history, and the nature of the universe we inhabit. So when we look up at the night sky, we are not just seeing distant stars or faint galaxies. We are seeing a small portion of a much larger reality, one that extends far beyond what we can observe, and perhaps far beyond what we can fully comprehend. And still, we continue to look. Not because we expect to find a final answer, but because the act of searching itself brings us closer to understanding. In a universe that may have no edge, no true beginning, and no final boundary, the horizon is not just a limit. It is where curiosity begins. If the future of the universe points toward isolation and fading structure, there is another layer of reality that operates on scales so extreme it almost feels detached from everything we have explored so far. It is not about galaxies or stars, but about the stability of matter itself, and whether the building blocks of reality are truly permanent. At the heart of every atom lies the proton, a particle so stable that, for all practical purposes, it has been treated as eternal. Everything we see, from planets to living organisms, depends on the assumption that protons do not decay. Yet some advanced theories in physics suggest that this stability may not be absolute. Over extraordinarily long timescales, far beyond trillions of years, protons may slowly break down into lighter particles. If this process, known as proton decay, does occur, it would mark a profound shift in the universe. Matter, as we know it, would begin to dissolve, not violently, but gradually, as atoms lose their structure. Galaxies, already dark and quiet, would lose even their most fundamental components. The remnants of stars, the cold remains of planets, and even the particles drifting through space would slowly transform into radiation and elementary fragments. This would not be an event that happened suddenly. It would unfold over timescales so vast that no observer could witness it as a single process. Instead, it would be a slow erasure, a steady reduction of complexity into simpler and simpler forms. By this stage, the universe would already be cold and sparse. Energy would be thinly distributed, interactions rare, and structure minimal. Proton decay would simply continue the trend, pushing the universe further toward uniformity, further toward a state where nothing meaningful can occur. Yet even this may not represent the deepest level of change. There exists a more unsettling possibility, one that arises from our understanding of quantum fields. What we perceive as empty space is not truly empty, but filled with underlying fields that define the properties of particles and forces. Among these is the field responsible for giving particles their mass, and, according to some interpretations, the state of this field may not be perfectly stable. If the universe currently exists in what is known as a metastable state, then it is possible, however unlikely, that it could transition to a more stable configuration. This transition would not happen gradually. It would occur as a sudden shift, forming a region of space with different physical properties. This is the concept of vacuum decay. If such an event were to occur, it would begin at a single point and expand outward at the speed of light. Within this expanding region, the fundamental constants of physics could change, altering the behavior of particles, forces, and even the structure of matter itself. Everything within its path would be transformed instantly, not destroyed in a conventional sense, but redefined according to a new set of physical laws. There would be no warning. Because the transition propagates at the speed of light, it would be impossible to detect before it arrives. One moment, the universe would exist as we know it, and the next, it would be entirely different. Despite how dramatic this sounds, it is important to recognize that this idea remains theoretical. Current observations suggest that if such instability exists, it is extremely unlikely to occur within any meaningful timescale. But its possibility highlights something important about the universe. Even the laws of physics may not be permanent. They may simply describe the current state of a deeper system, one that could, under the right conditions, change. This introduces a different kind of uncertainty, not about distant galaxies or the far future, but about the foundation of reality itself. It suggests that the universe is not only evolving in terms of structure and energy, but that the rules governing it may also be subject to change. When we combine this with everything we have explored, the expanding horizons, the fading of stars, the growth of cosmic voids, and the possible endings of the universe, a consistent picture begins to form. The universe is not static at any level. From the largest structures to the smallest particles, everything is in a state of transition. Some changes are slow and predictable, unfolding over billions of years. Others are theoretical and uncertain, existing at the edges of our understanding. But all of them point to the same underlying truth. Nothing is fixed. Not the galaxies, not the stars, not even the particles that make up matter. Everything exists within a system that evolves, shifts, and transforms over time. And this brings us back to one of the most fundamental ideas we have encountered. Limits. The limits of observation, defined by light and expansion. The limits of interaction, shaped by horizons we cannot cross. And now, potentially, the limits of stability, governed by the underlying structure of physical law itself. Each of these limits reveals something different, not just about what we cannot access, but about how the universe is structured. They are not barriers placed at random, but natural consequences of the way reality operates on both cosmic and quantum scales. And yet, even with all of these boundaries, there remains a sense that we are only seeing a fraction of what is truly there. Because every time we identify a limit, we also uncover the possibility of something beyond it. As we bring these layers together, something deeper begins to take shape. Not a single answer, but a structure, a way of understanding how all these pieces connect. The observable universe, the horizons that define its limits, the vast voids that shape its structure, the long future that leads toward darkness, and the uncertain origins that sit beyond our current theories are not separate ideas. They are all expressions of the same underlying reality. A universe governed by rules yet not fully revealed. What we see, from the smallest particles to the largest cosmic structures, is only the portion that can be accessed within those rules. Light travels at a finite speed. Space expands. Energy disperses. These are not obstacles placed in our path, but the natural behavior of the universe itself. The limits we encounter are simply the result of these behaviors interacting over time. This means that the boundary of the observable universe is not a fixed edge, but a moving relationship between us and everything else. As time passes, new regions become visible as their light finally reaches us, while others fade away, slipping beyond our event horizon. The universe is constantly revealing and concealing itself at the same time. In this sense, observation is not about seeing everything that exists, but about seeing what is currently accessible. The same applies to structure. The cosmic web, with its filaments and voids, is not a random arrangement, but the result of matter responding to gravity over billions of years. Dense regions grow denser, empty regions grow emptier. The universe separates itself into contrast, into patterns that reflect its earliest conditions. Those initial fluctuations, almost imperceptible in the beginning, are still visible today in the distribution of galaxies and the faint imprint of the cosmic microwave background. Everything we observe carries a memory, not in a conscious sense, but in structure. The present state of the universe contains information about its past, encoded in temperature variations, motion, and distribution. By studying these patterns, we reconstruct a timeline, not by witnessing it directly, but by interpreting the evidence that remains. And yet, this method has limits. There are events we cannot observe, regions we cannot access, and conditions we cannot recreate. The earliest moments of the universe, the exact nature of its origin, and the full extent of its structure may remain permanently beyond direct observation. Even the tools we have developed, powerful as they are, operate within the same boundaries imposed by physics itself. This does not mean the answers do not exist. It simply means that our ability to reach them is constrained. The future introduces a similar pattern. Just as we cannot see beyond certain horizons in space, we cannot fully experience the far future of the universe. We can model it, predict it, and understand its likely direction, but we cannot observe it unfolding. It exists as a continuation of the same processes we see today, extended across timescales that stretch far beyond any possible experience. And those processes are consistent. Expansion continues. Energy spreads. Structure fades. Whether through the slow progression toward heat death or through more dramatic possibilities like vacuum decay, the universe moves toward states that are simpler, less structured, and more uniform. This is not a collapse into nothingness, but a transformation. The universe does not disappear. It changes form. From a dense, energetic beginning to a structured and complex present, and eventually toward a state where complexity becomes increasingly rare. It is a progression defined not by intention, but by the laws that govern energy and entropy. Even the most extreme possibilities we have considered, the tearing apart of structure or the reconfiguration of physical laws, follow this same principle. They are not exceptions to the rules, but consequences of them, expressed under different conditions. And this leads to a perspective that is both simple and profound. The universe is not something with a clear edge, a defined beginning, and a final endpoint in the way we might expect. It is a system that evolves according to consistent principles, where limits emerge naturally, and where every state leads into the next. We exist within one phase of that process, a phase where stars still shine, where galaxies are still visible, and where the evidence of the universe's origin can still be detected. This moment, in cosmic terms, is not permanent. It is temporary, positioned between a past that we are still uncovering and a future that will gradually obscure it. In time, the clues we rely on today will fade. The expansion of the universe will carry information beyond reach. The sky itself will change, becoming simpler, darker, and less informative. Future observers, if they exist, may not have access to the same evidence we do now. Which means that understanding the universe is not just about space, but about timing. We exist at a point where the universe is still readable, and that, in itself, is something rare. When everything is considered together, the scale, the limits, the evolution, and the uncertainty, the universe reveals itself not as a complete picture, but as an unfolding one. At every level, there is more than what we can see, more than what we can test, and more than what we can currently explain. But this is not a flaw in our understanding. It is a defining feature of the system we are trying to understand. The observable universe is not the whole universe. The present moment is not the final state. And the theories we have today are not the final description of reality. Each of these is part of a larger process, one that continues beyond our current reach. What makes this process remarkable is not just its scale, but its consistency. The same principles apply everywhere we can observe. The same laws govern the motion of galaxies and the behavior of particles. This uniformity allows us to extend our understanding outward and backward, building a model of the universe that, while incomplete, is deeply coherent. And yet, coherence does not mean completeness. There are still gaps, still unanswered questions, still boundaries that cannot yet be crossed. We do not know what lies beyond the observable universe. We do not know the true nature of dark energy. We do not yet have a complete theory that unites gravity with quantum mechanics. These are not small details. They are fundamental aspects of reality that remain unresolved. But the absence of final answers does not diminish what has been achieved. It highlights the progress that has been made. From a position of complete uncertainty, humanity has developed the ability to measure the age of the universe, map its large-scale structure, detect the remnants of its earliest light, and predict its future